is Roberto Fernandez, University of Rouen, and his title is right up there.
Yeah. Okay. Thank you, David. So, as you see, I'm reporting on a collaboration with Aldo and Benedetto. In fact, what I like to, this is going to be a comparatively simple talk, and I expect it to be self-contained. This is on the one hand, you could see these results as an application of this new criterion that Aldo talked about yesterday. But in fact, so there are three reasons behind my message. One is an application. First is an application to non-countable set of objects. Okay, the spheres are not countable. Yesterday, everybody was summing. These have to be integrated. This, in a sense, is a small change, okay, which you could imagine by yourself. But on the other hand, also it's also an application to a case where the graph, the incompatibility graph, is of infinite degree. So in a sense, it's a not so trivial application. And the third aspect is that I would be able to show you an alternative proof of our criterion. I'm not going to use, I don't want to obtain my result. Certainly a consequence of the criterion discussed by Aldo, but it can be proved independently with a special trick in this case. So that makes it simple. So what is the basic setting? I'm talking with a classical continuous gas. So as this is an mixed audience, I'm going to introduce what I mean, define what I mean. So basically, I'm thinking in particles moving in some continuous space, typically is RD. And initially, I considered a fixed box. Okay. Of course, eventually, I may be interested, and I will, in the thermodynamic limit. That means that the box goes to the whole space. Now, this is classical, so the particles are considered to be distinguishable, but you don't ask which particle is where. You rather ask questions as whether there are particles at some region or not, but you don't care which. So what is the configuration space? The things you have to keep track of are, for each particle, you need the momentum, and the position of the particle. Okay? Momentum is speed times the mass. And there will be a 1 over n factorial that comes from the fact that you don't distinguish which particle is where. So in order to set up the measure you are going to use, you have an energy function which depends on the momenta and the position of each of the n particles, if you have n particles. And this is the kinetic term defined by the momenta. And then there is some interaction energy, which also we call it the configurational Hamiltonian, only depends on the configuration where the particles are, which takes somehow the usual form of sum of local terms, in the sense that they depend on as a finite number of bodies, okay, finite number of particles. And then you add to that what is called a Gibbs chemical potential, which acts as a field. It's like the analogous of a magnetic field in this setting. So all in all, you are going to consider some measures that, in fact, the measures are on finite families of configuration. So you only consider the presence of finite families of particles at each time in the box. And the projection on the case in which you have n particles is, okay, it has the activity of each particle. So this is the Gibbs free energy, and the Gibbs chemical potential. Then this is the factor that comes from the kinetic part, and then the configurational part. The normalization is, of course, this normalization here. This normalization, you have to sum over all possible configurations of finitely many particles with its own weight, and this is n factorial that I told you about. Now, if you are not going to ask questions about momenta, if you only care about observables that depend on the positions of the particles, then the momentum degrees of freedom can be integrated out once and for all. And just give a factor, for each particle, each I, which you can group it with the e to the beta mu that was coming from the Gibbs energy, chemical potential, and you end up with an expression that looks very much as the one we have been dealing here, only referring to the configurational part, except that the sum over objects is replaced by an integral over objects. But it's a change that you could imagine. Okay, and this is the new fugacity of the whole system. Okay. Now we're going to deal with gases of hard spheres, so we're going to interpret these positions as the centers of spheres of a given diameter. R is the diameter. And the energy, using a little bit the physics notation, is either infinity or 0. So the weight factors are either 0 or full value. Infinity, if they try to interpenetrate, they cannot. Okay? And otherwise, there is no other interaction. They're just spheres that cannot get one into another. That is to say that the measure that I wrote before, this exponential factor becomes a product of indicator functions, asking for each pair of centers to be at least at distance r. And the normalization is the corresponding sum over all things. Okay? So this maps us into one of these polymer systems where the polymers are these centers, are points in lambda or in RD, and the compatibility relation is simply not the intersection of the spheres centered on them. So it's a natural extension of what was proposed yesterday. And of course, we are interested in the pressure, 1 over the size of the box times the log. And then the cluster expansion is to write the log of this partition function as a sum of the same form as the partition function, okay, with including the factorial, where there are some coefficients here that carry the whole weight of the transformation from function to log. Okay, so is the log. I prefer to write it this way because that's the way you obtain it. In fact, okay, these functions that define these cluster expansions are the truncated functions that you have seen already many times. Now, the standard way to estimate the radius of analyticity is to take absolute values. Okay, so you want to, in fact, you want to take absolute values throughout and to obtain a lower bound on the radius of conversion that is uniform in lambda. Okay, this way you know that this analyticity will go through the limit, to the limit, and then you don't have a phase transition if you are a statistical mechanics guy.
Definition of the left-hand side.
This is the definition of the left-hand side. Okay, this is
Actually, absolute value.
no. Okay, I'm just using no. So if you don't like it, put a bit in. Yeah. Okay. In fact, it's the pressure for a negative fugacity, which is unphysical. Okay. So, well, we have seen already these truncated functions. So what do you do? Well, now just for a change, I use lowercase g's for graphs. They were always in uppercase before. So you take your polymers in the language of yesterday, or your points, centers of spheres, and you draw a graph with it. The graph has as vertices 1 to n, so the labels, not the centers, the labels. And you connect a pair of labels with an edge if and only if the centers are violating the constraint. Okay? So it's an incompatibility graph, if you want. And then what you have to do, you have to sum over all possible subgraphs of this, which are connected and spanning. It's what is understood that the graph itself has to be connected, otherwise the contribution is 0, the graph x1, xn. And for each of these subgraphs, you do this, you add this factor, which is -1 to the number of edges. So you see the basic, problems of these expansions that they involve a huge number of cancellations. This is a huge number of terms that are 1 minus 1, 1 minus 1. I have to be careful who wins. Okay, and you cannot just put brutally absolute value inside because it is too big a number and there is no hope to get a non-zero radius of conversion. And those configurations of centers that give a non-zero value for these truncated weights are called clusters, okay, of spheres. And in particular, you know, and they have to be, for this to be true, they have to be connected. In fact, if they are not connected, then the phi t's are 0. Okay, now what are the results that exist? Now I can use the check criterion here, even if it was not proven originally in this setting, but you can prove it anyway with a different proof, and the criterion is true. So in one of the ways that it was written,
What is this first word?
that's a wrong way to say check. How do you spell this? The second C, check. Okay. I knew how to write Czechoslovakia, but then I didn't know how to write Czech. No, I'm saying the Czech because of the discussion yesterday whether this criterion is Koteski prize or the unknown student that did it first. So, as the Czech models, then okay. Okay. So the criterion, one of the ways was written yesterday, is that the absolute value of the fugacity has to be, they have to find a mu such that this quotient is positive, and then whenever you find the fugacity is bounded by this, for some mu, then you have convergence. And what is this function? Well, this function yesterday was, you have to sum over all the polymers that were incompatible with a given polymer. Here the polymers are the points, which are the centers of the spheres. By translation invariance, we can consider just the origin as one of the spheres, and we consider the sum over all the configurations that the possible polymers that the possible spheres that intersect the origin. This is this integral. Okay, so this gives you just the volume of the d-dimensional spheres of diameter r. I'm sorry, this is a misprint. And then, you see that here this function depends in fact of the product v times mu. So if you multiply by v both sides, you end up with this criterion. You need that c times v be less or equal than the max of a times divided by e to the a, and this is 1 over e. Okay, and that's an old criterion. This is we call classical, which is already in Ruel's blue book. Okay, 67, I think, was something like that. But he proved it using Kirgus-Salv. But you can do it with all the other criterion we learned since then.
Presumably he had a less than sign and you have a less than or equal to sign? Or?
It could be that he has a less here. But anyway, as when you take the supremum, you are forced to have a less here. So I don't think that he got. I'm not claiming an equal here, because you need a mu. And
it's true with equal. It's true with equal, but you don't usually care about a series converging, whether or not it converges on the boundary. But you're interested in analytic functions and over.
With the equality is true, but in absolute sense also no. Yeah. Okay.
True, but you never use it.
Because some of one opponent something like that.
Okay. Well, anyway, I mean, I just want to use the straight criterion and then. Okay, so let's see what we gain with our criterion. So remember, then our criterion is exactly of the same form. So it's like this. In fact, all the criteria were discussed here were of this form, but you are just changing phi for something smaller and smaller, so it allows you a bigger radius of conversion. So now our criterion, you replace this exponential by what we call the partition function of all the spheres that are incompatible with the sphere centered at 0. So you have to consider sum over all possible collections of finite connections of spheres. These are the centers of the spheres. They have to be incompatible with the sphere centered in the origin. That's why this. But then, due to the part of the Penrose conditions that we keep, the centers of the spheres, this is a misprint, this should be without bracket, have to be, and this is another misprint, has to be separated by R. Sorry, has to be larger than R. Okay, so the children of a vertex have to be compatible between themselves. So given that before we learn that the V will appear, then let's change variable here, multiply and divide by the volume of the sphere, and our criterion ends up being like this, where the function here, we go to spheres of radius 1, and it's a sum over all possible cases. Now this a to the k, which is will be the product of mu times the volume, in fact, but anyway, I want to take the max, or the max. Okay, and here are the conditions. Okay, this integral has to be done under the condition that each sphere touches the origin, and they are farther apart. They don't touch each other.
You probably said it, but that's a misprint, right?
Yeah, there are two misprints, several misprints, in fact. See, this is a misprint, this is a misprint.
The inequality, right?
The inequality here is reversed.
Yeah.
But then aren't there two more misprints? The mu in the numerator is A, and the max is min.
This is an A, and the max is max.
The max is max.
You may want it soup, but it's going to
Oh, I'm sorry, it's max. Right. It's the best, right? The best is max, sorry.
So I did that to check whether you were awake. I mean,
You can't expect us to be awake.
yeah,
this
I
hour.
cannot. No, I know. No. Okay, so now the thing is that these integrals are not immediately to perform, and we saw something like this yesterday. In fact, some of them can be transformed, can be done with the aid of Bessel functions. I don't know whether all of them. Otherwise, you do it numerically. But anyway, to a trustable approximation, that's the right-hand side for our criterion versus the 1 over E that you have for the
in dimension 2, were you
Dimension
able to do
2.
it analytically?
This is dimension 2. This is the radius of analyticity.
No, but I mean, can you actually do those integrals
Yes,
analytically in dimension 2? It's some Bessel integral or something?
It's even simple.
No, but there are several integrals. Let's see. The first one is simple, but I'm not sure.
In 2 dimensions.
But you see, the point is that when you start doing these integrals, I mean, you have to care for the first 1 or 2. K equal 1, k equal 1 is easy. K equal 2, k equal 3, and then it becomes ridiculously small.
I was just wondering whether you could compute CD of A exactly.
Probably with the techniques of yesterday of Labelle, this long integral. That would be nice to check their exact expressions with this, which are approximate anyway.
So what are these graphs? The graphs, in the language of yesterday, the graphs you have are a complete graph on k vertices and one more vertex.
Yeah, as he had.
But you have, it's these Riehofer integrals where you have the Mayer factor f on some of the things and 1 plus f on the others. Because you have an incompatibility and a
But
compatibility.
Mayer factor is 0 infinity here. So.
Yeah, so it's the level 3, eh?
Yeah, no, I know, but I mean, some of the edges have a compatibility, and some of the edges have an incompatibility.
Yeah.
I think what Anna was calling a Riehofer integral, as
So
opposed to.
what you were saying that there are somehow bigger and bigger k, smaller and smaller.
Contribute less and less.
Right.
in some sense.
And this you cannot somehow, because this would be just using standard condition, but somehow with this dependence on the size, somehow this would.
Yeah, maybe. I mean, that I certainly I did. I didn't want to get into that. No, I'm very happy to thank all people that did it. But yeah, you see the point. I don't know whether it pays to estimate this in some sense, or anyway, or maybe improve the criterion.
In every
no?
dimension, this is a finite sum.
Yeah.
Yeah.
You can't fit
But,
a certain
yes.
number, past a certain number of particles.
So in 2 dimensions, what is you get to 4 or so, or 5? I think to 5. But anyway, I mean, to do the for 6 is already some work. But yeah, you could do that. But in practice, it drops very fast, very fast. Okay, so that's what you gain with the criterion. Okay. So now what I would like to do is, in what is left, is to discuss the proof of our criterion in a completely self-contained way. I mean, I'm not gonna. I will use the Penrose identity but then I will not use this summing over trees that okay, not the same sums that we saw yesterday. At least. There will be a further trick. Okay, it's a simple alternative. So let me go back to the Penrose identity. So this is the heart of the problem. Estimate this alternating factor, which is severely alternating factor. So here you take just any graph which is connected and you do the sum. And then the Penrose identity tells you that you can find a family of trees. In fact, Penrose chose one particular family which seems to be particularly well suited for our problems, but there are other ways. Such that this becomes an identity. So you get the alternating sign property and an exact estimation of the absolute value of the sum, which is the sum of the trees. Now, from these trees, we're going to keep only one condition, which I'm writing this. So I'm going to just discuss this condition, not the full definition of Penrose tree. So a tree is a Penrose tree if it is a weak Penrose in yesterday's notation, if it has the following two properties. Well, first of all, one property. First of all, you fix one vertex as the root. This is part of the Penrose prescription, so you have to fix the root. And then you consider the descendants of each vertex. When you look the tree as a rooted tree. And the condition that we are going to keep, which is only half of the conditions of Penrose, is that if you have an edge in this tree, so this is the mother, say, and this is the descendant, then first of all, the edge has to be an edge present in the graph, but the descendant themselves, the brothers, cannot be linked in the graph. They cannot be neighbors in the original graph. Okay, that's the only condition we keep, because this makes the estimation, the trees are weighted with a vertex weight given by this condition. And this gives an expression which is easy, in fact, to sum in a recursive manner, as Aldo discussed yesterday.
And this is a necessary condition.
This is necessary.
And so if should read only if. This is a superset.
Necessary condition, yeah.
This is a superset of the
So this is bigger. So this is why you are going to, the absolute value that we want is going to be less or equal than the number of trees satisfying this condition. So it's going to give me a small region of convergence. So in our case, so okay, these are the sum that we obtain. So you sum this sum over graphs becomes the sum over trees satisfying. Well, here I write it in this decomposed way. So I sum over all trees, and then here is the test whether the tree is acceptable or not, given x1, xn. For the tree to be acceptable for our restricted Penrose condition, or weaker Penrose condition, you have to have that for each vertex, all the descendants are at a distance less or equal than r, because they have to be linked in the original graph, they have to be incompatible. They have to represent spheres that collide with the sphere centered at the vertex B. However, all the brothers, all the centers that are descendant of B have to be themselves farther than r. Okay, so this is the test to see whether we accept the tree or not. Okay, now if you do for the classical proof, this part is what is missing in the argument. Okay, this is what is in the traditional approach. This is forgotten. The only thing you have is just trees such that descendants are linked by incompatibility, but you don't impose any further constraint between them. Okay, so in all what I'm going to do now, just by forgetting the second one, we will recover the classical result. So we are going to consider then this majorizing series, in which here this sum, this term is an integral, in fact, is testing for all possible choices of x1, xn, whether the tree that you are summing is acceptable or not. Okay, now usually here you switch to the degree. The degree is the number of descendants if you are at the root, and the number of descendants minus 1 if you are further up. because you have a father or a mother, okay, which is one of your, which is part of the degree. So I repeat here that given each vertex, its neighbors are a distance less or equal than r, but keeping a distance strictly less than r1, doesn't matter, between themselves. And what we will, for each, the first vertex can be anywhere, okay? And for further vertices, anywhere in lambda, in fact, the first one. And for further vertices, we are going to even forget that they are in lambda because they are just going to keep this relation with the previous vertex. So this is an approach. So if you consider this testing sum of a given tree becomes, can be majorized by a product of integrals. So the root, or the integral is here. This integral is telling you that for each of the descendants, they have to be closer to r, but themselves they have to be larger than r. And this has to be satisfied for each of the vertices of your tree. And okay, this d is the number of descendants that you are having, which is d1 for the root and d minus 1 for the others. So this is the key step to visualize this relation. That this test, you can do it vertex by vertex, and in each of them you have an integral that doesn't depend on anything else. Well, following the idea of pulling out a factor of volume, then okay, you just change to unit spheres with the convention that if k is equal to 0, all that is equal to 1. And then one observation is that this tilde g is less or equal than 1. Okay? If you forget this constraint, the second constraint, if you are in the classical case, then this is exactly the same as the denominator. So you get 1. Okay, so this corresponds to the classical bound.
You want unit volume or unit distance?
Sorry? Is unit... yeah. The radius has to be 1. Okay.
Yeah, normalize the radii to be 1 and pulled out the right one.
I think I'm thinking...
Factor.
So you pull down just RDK.
Sorry?
Just RDK, which comes out.
Yeah. Okay.
Oh, I see. That should just be argued.
Yeah, you are saying that here because you are taking...
No.
No, because you are if I take RD, then this is... No, this is... I'm comparing the volume of... Take 1 only. The volume of the sphere of radius 1 and the volume of the sphere of radius...
Well, but the
This
substitution
is
given
R. I'm sorry, this is R. This is R. Yes.
R to the k.
This is R. Yeah. Okay, so you do this. Now you use the fact that the degrees add up to 2n minus 2, so you group all the facts, and then you end up with these integrals over there. And then you see that for each tree, the only dependence you have in this upper bound that you obtain is through the degree, and nothing else. So when you sum over all the trees, then you just have to sum over all possible trees that have the given degrees. Okay, that gives you this extra term here. Okay, here I'm the previous sum. I'm summing over all the degrees and multiply by the Cayley factor. Okay, so this is trees with the given degree. You put everything together, and
Can you go back for a second?
yeah.
These are labeled trees?
Yeah.
Yeah.
This one?
And so this D1 through Dn is a degree sequence
Yeah.
ordered.
Yes, because you have the labels are fixed, 1 and n.
Appendix 1 of degree.
1 up to n.
Okay.
They are not ordered here. The degrees are not ordered.
I think they are.
No, no, they are.
D1 through Dn are separate
maybe
sums.
some-
Yeah, yeah,
No,
because
I mean the
not the
It's
size.
an ordered n tuple, D1
Yeah,
through
Yes.
Dn.
Yeah.
But, and so you're asking if you have a tree with those degrees, how many ways can you put, I mean, the descendants of is the root is always number one?
One, yeah.
But
The
the
root
other
is fixed.
guys can be labeled anything.
The
That's
descendants can be.
convention?
No, you have label 1 to the n. You say the label 1 have incidence number as degree D1.
Oh, I
the
see,
label
because-
2,
because
how
this
many
is-
tree I can.
Oh, I see, because this is.
Here, I'm not looking to a particular tree here. I'm just have set of vertices under degree in whatever the tree is. Okay, so this Bn there, if you forget this last constraint of the sum b2n minus 2, then you can write it as just, well, there is a factor n minus 1 that comes from some mismatch between the factorial there and the factorial there. And then the rest is just a product of exponentials. Okay? Each one of these will give you an exponential. Okay? So this is what I wrote as CD1. Okay? And so the final bound is will be this, okay? Which converges if this thing is less than 1.
What again was CD of 1?
CD of 1 is the integral okay. Let me see. How do this is some with the
Generating function for the G.
for the
Oh, so the generating function, but evaluated at a equals 1. And later you're going to improve this to allow.
yeah,
to
that's the
evaluate
extra
at the
trick.
end.
So they are already
I think what happened was that the radius of the spheres was not 1, the volume of the spheres was 1.
the distance. So the radius is 1/2. Yeah. What?
I think what happened, well, for example, in that formula is that the radius of the spheres is not 1, it's the volume of the spheres which is 1. Because I think you wanted to factor out the volume of the sphere.
Yeah. Yeah, I want to factor in various
You
ones.
need
So-
to do substitution not by r, but by some r times
R
square
over pi
times
or
the root
something,
of the volume.
This is what we say.
Hmm?
This is what we're saying.
Yeah, I want a factor there so that the GD becomes.
Well, you want the volume out the front, so if you want the volume of the sphere out front, then you have to be integrating over units, over spheres of unit volume rather than spheres of unit radius.
Okay, so this is wrong. This
Otherwise,
one is
yeah,
Yes.
otherwise you won't
This is
have
also
this.
wrong. This is R, but yeah.
Yeah, otherwise
So
you
this
won't have
radius-
this estimate that GD tilde is less than 1 or something like that.
Yeah. Okay. So then we have to check the integrals again. They are even smaller. Well, no. Okay. Anyway, so we end up in this type of constraint for this to be less than 1. If you replace this by 1, as it will be the classical case, then you end up not CD by 1, the G tilde by 1, then you get an exponential, and you prove in this way the classical case. Okay, CD, if you put CD is a sum of 1 over n factorial, the Gn tilde. Okay, if the Gn tilde are bounded by 1, then the 1 over n factorial gives you the 1 over e, and you get the classical result. Now, here is the trick. This is a trick that has been used to show, before to show that you could prove Kotevsky-Pride-like condition in the classical way by summing the leaves of a tree. Okay? And it's a very simple one. You just multiply and divide by a factor of a. Okay, that I wrote it in this way. You put a to each degree, and then here is a to the minus 1 because the sum of the degrees has to be, the degree is 2n minus 2, but there is a minus 1 here that subtracts an n minus 1, okay, because only in here you have. Okay, and this a is to be determined. And then you do this exactly the same argument.
So you use the constraint on the sum of the d's to make sure that
Yes.
the number of a's you're
So
putting in
that's the,
and then you throw
and then
away
I
the
forget,
constraint.
but I keep this a. So it's a very, and then you get exactly the same as before, but now you get a here coming from there, and the CD of a, which is the result of the sum with the factor, with the power a that I wrote at the beginning. Okay, so that's how we get this criteria. Now, the nice, well, the nice, that's in a sense surprising, is that with this trick we get to our condition. Okay, the one that still we cannot prove inductively, but this is being proven pretty much in the same way as the classical way, with a little more care in the Penrose condition, and this extra trick of the A. Without the extra trick of the A, then we would be getting an improvement anyway, because this is better than E, but not our improvement. Our improvement requires this extra A. In a sense, for the time being could be a curiosity, but this gives a complete, a different way, in a sense more simpler, but of course there is a trick there, to obtain the result, and which, you see, what makes it work is the fact that somehow there is this VDR, the size of all the contours is bounded. The size of my objects, it's a bounded thing. So whenever you have a combination, a polymer expansion in which the polymers have a fixed volume, then I'm pretty sure that you can use this trick to reobtain our condition rather than the original way obtained.
It's simpler in some ways and less simple in others,
Yeah.
because you're avoiding the use of the generating function for identity for rooted trees, which is very simple. And instead, you're using the specific Cayley counting of trees by their degree sequence, which is in some sense more complicated.
Yeah. So the test will be, for instance,
Taste.
for somebody that hates cluster expansion, which is the system they would prefer? And you are a perfect example.
I think I like the recursive way better. I mean, because there's a simple formula, right? That says that the sum over all the rooted trees is a root plus a bunch of rooted trees underneath.
Yeah.
But does this tell you more about the structure of the
It tells you more about the structure of the trees, but since you don't care about the structure of the trees.
Well, speak for yourself.
Do you do care?
I love trees.
Okay, that's it. I mean, that's all I want.
So are there any questions besides the ones that many ones that have already been asked? Well, in that case.
One
yeah.
question. In one dimension, you not only know the classical bound and your bound, you know the exact answer.
Yeah, that would be a nice.
What's the story in one dimension?
Don't know. I didn't check.
I mean,
I was not.
because in one dimension, probably you can do your CD of A integrals
Yeah, that could-
exactly, right? It's
In
counting.
one,
So
in one dimension, you can
Oh, it's
really
easy.
compute the real. You can determine the internal trees exactly without
This approximation.
this inequality. So you don't have to relax the condition. You can do the thing exactly.
Yeah, but the question is how far off. we
Yeah,
are.
you're right. I mean, right. That's the combinatorial way of getting the exact solution of the one-dimensional gas, which is n minus 1 factorial, I guess. But you're right. It's just the only cases are k equals 0, 1, and 2. Because with a rod, you can at most
Not
put.
even 2, huh?
Yes,
Instead
you
of
can
you
put-
measure 0.
What?
Measure 0 if you put k equals 2.
Why? No, because you can have a rod of length 1, and it can overlap two other rods
Three would be
that
a
don't.
measure 0.
What?
If you put one, then 3 things. You put 1, you can put.
Yeah, 3 would be
That's
measure
right.
0, yeah.
You can put 2.
You put 2, so it's just some simple rational numbers. It'd be interesting to see how does it compare to the exact answer.
So
So maybe I am going to ask a stupid question. I try to understand the family of Penrose tree.
Mhm.
Because this condition you necessary and sufficient is not. There is different family of trees which can satisfy this. I take example of a graph with 4 vertices like this. Tuck, tuck. This is the root,
Yeah.
and I go. So I can take 2 trees. Check, check.
Yes.
Oh, check, check.
In this case, yes.
So there is two choice.
well,
So it's not,
yeah, but
it's
they-
not canonical.
No, no,
But
no,
you have to be-
The,
but,
the
like,
Penrose,
they
the
have to-
Penrose scheme is one possible choice. Let's say, but usually the unique choice.
Yeah, so it's not.
And so the way, I mean, let's see if I understand the question. The way to partition
Yes.
the graphs in terms of trees is far from unique.
Yes, it's a.
Penrose chose this one, which is good for us, but that's all.
So maybe
In
that's
my example, which one you
Yes,
choose? You need the order on the.
So
the
the-
one with the one with the lowest number. If we
So let's see. What is your example? So you have what? What is your graph? Is this?
Check,
4.
check, yes.
Yeah.
The root is on the.
So that's you call one.
Okay,
Okay.
so there is 2
So
different.
so then you have to be spanning.
Oh,
This it cannot. Let's see. This
Yes, but this
you
is
have. Well, for us, yeah, this is fine.
Roberto,
Yes,
you have
but-
to put label to the
yes,
side.
you have to
Yeah,
link
okay,
2,
let's-
3,
that
4,
one
For
forget.
example, 2, 3, and 4.
yes, but there is a second.
Then there is the second condition.
Yes,
Okay,
and-
the second condition will choose between one of two because you have either this or that. Okay, so if I did this 2, 3, 4, then this is. Yeah, let me see. This is.
So you have to make a choice.
This is-
between the
Yes,
two.
This is okay.
You take the median.
Ah, yes.
You can take. Yeah.
Because,
You have to. The second condition precise is the one that makes a choice between these two.
because after my talk, I try to understand. In fact, the object is a pyramid. The real object, and then from this pyramid there is a projection with trees, and because this process of going down and down, it's process of going level by level from the top of the pyramid and going down.
That's right.
So you have to select some edges where two pieces are working, and so the pyramid gives by itself the whole constellation.
But in
You
your
have no more
estimate, you do not
constellation,
make
and
a
then you have to
choice. You
choose a
simply
tree
count most
among
of
the
them.
pyramid. And this
In this case, in our estimation, yes, because we only look to what happens here. We don't
So
look
you
what
count
happens
both
from
of them as a.
So this is
So you make a choice, and each time you take, for example.
you should. We are not.
The map
They
is
are not.
We are
They're
not.
coming over everything.
We are not. In
They're
our
coming over
case,
all.
we are not because your problem appears one generation between
Yes, we
two
can-
different
exactly.
generations.
This we are throwing out. These
Yes, and you say it's one.
No,
No.
In order to define Penrose tree, they have to make a particular algorithmic choice of which one.
Yes.
But they're actually doing their bound in terms of what they call weak Penrose
Yeah,
trees,
so the weak
which is
Penrose
a
are
larger
both.
class
So
that
you
includes
select all of
both.
them?
Yes,
Yeah.
with once we
yes.
have the Penrose trees.
It's an upper bound.
Ah, yes.
This is what he in his talk.
Ah, okay.
You
But
see?
so one more question, Roberto. So in general, what you can do is take any partitioning in the sense of Penrose, so one of those maps,
Yep.
what Olivier yesterday was saying, T to T plus, right? And you take any map from trees to guys higher in the lattice such that you've decomposed the connected spanning subgraphs as a disjoint union of Boolean intervals. And then you look at the trees that have the property that T plus equals T.
Exactly.
And you used a particular construction of that partitioning due to Penrose. But you could imagine using other partitionings. Of course, if you had used all the conditions in the partitioning, it wouldn't have mattered because you would have counted exactly the number of these R of T equals T trees, which is the same whatever the partitioning is. But since you threw stuff away, it might be that there's some other choice of partitioning that you can estimate in a finer way.
Yeah, and could be even adapted for a particular problem. I mean, better adapted.
Well,
This is
actually,
to
yeah, I'd like to throw in a remark. I don't know whether it's possible, but if you can get a really good estimate on the radius of convergence, in other words, I don't know whether the actual radius of convergence is large enough, but there is this major problem, which is to prove the existence of a phase transition not at at the cat's limit, but near the cat's limit. Cat's limit brings you to mean field theory, where if you're in the limit, it's easy to show there's a phase transition. But to prove that there's a phase transition near the cat's limit could possibly pass through a really good estimate on a hardcore gas Meyer expansion. It's just the existing estimates aren't good enough, I think, at the moment to make those kinds of routes work.
Is there, from numerical work, an estimate of where you have to
Well, that's why I was asking that question earlier. I don't know what that, yes, I'm sure there is. I don't know what it is, though. Yeah. We should go on, though. Our next speaker, Professor Zarate. And integral equations for cluster expansion sums of polymer